Okay, so thanks again for the invitation. So today I'll talk about accelerated graph neural network inference. And since I guess I am the first talk, I'll go into a little bit more about the overview of what graph neural networks are actually doing so that we can talk about how we accelerate that. And I think I made too many slides, so feel free to, I'm okay with not getting through all of them. So feel free to interrupt with questions. And I don't know if I'll be able to see the chat very well, but yeah, feel free to interrupt. I'm happy to answer questions during the talk. So just to give kind of the outline, so I'll first kind of introduce where we are typically using GNN, so for HEP, trigger, and reconstruction, and then kind of go into what the GNN inference is actually computationally doing, and then what are the common challenges that are inherent in that for accelerating them. And then I'll kind of go into 3 different use cases or case studies for accelerating these graph neural networks. I know that the theme of the conference is tracking, but I went a little bit broader into different applications. Starting with particle flow reconstruction, graph neural networks for particle flow reconstruction, then jet tagging, and finally charged particle tracking. And then I'll kind of just try to summarize everything. Okay, so first, just to get everyone on the same page, overall, the picture of LHC event processing looks something like this. You have collisions coming in at 40 megahertz. Then, of course, we have a level 1 trigger stage, typically that's implemented on FPGAs and reduces the event rate by a large fraction. So in this case, these are numbers for the upgraded. Sorry, one question?
No.
Okay. No.
Go ahead. Sorry, we're going to mute the room because you may hear some people moving around.
Okay. Yeah. Okay. No worries. Yeah. So for the level 1 trigger, the output rate is 750 kilohertz for the upgraded trigger. This is for CMS for phase 2. After that, there's a high-level trigger stage. It's implemented on sort of commercial CPUs, and again reduces the rate down to something more manageable for computing, so 7.5 kilohertz. And then finally, we're of course doing offline processing and offline reconstruction and re-reconstruction. So often we'll be wanting to use GNNs in that framework too. The computing platforms for each of these sort of data processing stages can vary dramatically, as you can imagine. So like on detector, we usually have ASICs that are radiation hard to do computation. For the level 1 trigger, as I mentioned, there's field programmable gate arrays or FPGAs. For the high level trigger and for offline processing, up until now, the main sort of workhorse has been CPUs. But of course, now we're using a lot more GPU computing. And in fact, there's even people, we're even using now FPGAs for kind of co-processing. So sending, processing, offloading processing to FPGAs, as well as even actually other AI processors. So just to quickly recap, what are the differences between these different hardware alternatives? So the CPUs, of course, that we're all very familiar with, are of course the most flexible. They can sort of do any computation, but fundamentally it's mostly a serial computation, even though there's of course multi-core CPUs now and multi-core computing. Fundamentally, it's kind of a serial computation. So to get sort of more efficiency at the risk of lacking some flexibility, we can use sort of very, very parallelized multi-core processors like GPUs, which each core can do kind of its own arithmetic operation. And we can do this, over many, many cores so that we can sort of accelerate big computations this way. And this has been, of course, very successful for deep learning, where we have to do a lot of matrix multiplications. Similarly, we can do something similar with FPGAs. In this case, we're actually rewiring basically the circuit of the hardware for some specific tasks, such as matrix multiplication. And in this case, this can kind of improve the efficiency, but again, at some lack of flexibility, at the cost of some flexibility. So once you program it, it's programmed for that specific purpose. Of course, you can always reprogram it, but it's then tailored. And then finally, sort of on the end of less flexible, you have kind of ASICs, application-specific integrated circuits. And this can be, again, quite useful for when you know you have a task to do and it has to do that task for many, many years. And in fact, people are now starting to develop like deep learning ASICs, which we're even now starting to consider using for different kinds of processing. But of course, there's a risk in that if you really change the computation that you need to do, or deep learning is such a fast moving field, it can be a little bit risky to like tailor your hardware to specific models of computation when in a few years maybe the models can change. So for this talk, I'll mainly focus on GPUs and FPGAs, but as I said, actually, there's really actually some kind of interesting work to be done on thinking about these specific AI processors like TPUs and other more custom hardware. And so again, kind of to motivate why we're doing this, and why we're having this workshop, of course, the CPU demands are expected to explode as we go to the high luminosity LHC. This plot is old. Everything should be moved by essentially like 1 year back. But we expect the computing demands to explode once we go to this higher luminosity. So in run 2, the pileup, the number of tracks we expect looks something like this picture. Whereas in high luminosity LHC, of course, we expect much, much busier events, more complex, and these computing demands increase, very non-linearly with this increasing complexity of many, many pileup interactions. And the dominant fraction of this computing increase basically is both simulation and reconstruction, which so essentially cumulatively is about 87% of the total fraction of the total computing budget. And so we either need a much, much bigger budget and more processing power, or smarter algorithms like GNNs to try to keep up with these demands. And also, of course, using basically the answer will be actually combining both of these, using GNNs or using other algorithms plus the hardware that can sort of customize for that. And so, okay, why are we kind of thinking about graph structured data? The reason is because kind of it's a natural choice for high energy physics data. So it's, the properties of this data is that its measurements are kind of distributed in space and time somewhat irregularly. Overall, the events are usually sparse. So most detector channels are empty, but there's pockets of very, very high density. So we have to kind of consider both the fact that it's very, very granular, or you need a lot of detail, but it's also mostly empty. So basically gridding it up and using voxels is not always the best option. There's complex kind of interdependencies between measurements. So measurements like, let's say in a tracker and a calorimeter, we want to be able to kind of correlate these things. Physics objects, of course, can be composed of multiple measurements. So, we want to kind of look at the hierarchy of measurements, and not just, the low-level data, but also think about composite objects composed of those low-level elements. And then, of course, there's kind of inherent symmetries in this data. And the nice thing is that kind of graph or point cloud embedding of the data can handle these properties. And so this is showing kind of what that graph, one particular choice for that graph embedding of the data might look like. And as you can kind of even see from this picture, there's like a lot of choices that are already inherent in this, and those choices can lead to dramatically different computational performance. So I'll talk a little bit about that as we get there. Yeah, so in particular for tracking, the graphs you might construct, the hits in the tracking detector can be the nodes, plausible track segments can be these edges. And so in this case, you want to not have a fully connected graph where you connect all the nodes together, especially because the computational performance would be kind of the scaling would be really bad. Instead, you kind of want to reduce and keep only the most likely track segments essentially in this graph construction stage. Similarly, for calorimeter measurements, we can take these clusters of energies as nodes, and then the particle shower evolution as the edges. And again, there's kind of physical constraints that we can use to determine where the edges of this should be based on the geometry of the detector. For jets, the story might be a little bit different because it's not always clear, do you want to connect the nodes that are geometrically closer or closer in some latent space, or or even just fully connect the nodes. For jets, because there's sort of order of 100 constituents, it's actually often computationally feasible to just connect all the nodes. But this is another kind of choice that needs to be made. So that And finally, of course, edges don't necessarily need to be specified, but the graph connectivity can be learned dynamically. So it can be essentially this step can be part of the GNN architecture. And in that case, needing to accelerate that as like some accelerated kernel is also a challenge. Okay, so but I'll show kind of one example of representing HEP data as a graph. So this is just taking a jet and again, treating each particle in this jet as a node and then fully connecting those nodes. So you can kind of see this nice fully connected graph. Then of course, node features, constitute things like the particle form momentum. Edge features might constitute relations between pairs of particles, like the delta R between a pair of particles, so how far apart they are in the detector. And then there might be sort of global features you might consider for the whole jet, things like the invariant mass of all the constituents. And so once you have this graph structure, you want to apply this GNN to it. And so how does that look? The main ingredient of this is basically this message passing step. And so what that means is that, we have this graph, we have this node, let's say xi, and then we have a set of neighbors for that node, these neighbors j. So for all the neighbors j, what we want to do is basically compute a message via a neural network. So where we take in, where this neural network takes as input, basically a pair of these nodes. So xi and xj, and computes a single output or a vector of outputs. Then we have a sort of aggregation step. So we either sum or take a mean or take a max or minimum of all of these messages that are being passed from neighbors to this node. And afterward, we can take that summation and essentially from that compute an updated edge feature, updated node feature, this so-called HI. So essentially what we now have done is transformed this graph, originally the node features are xi, and sort of updated the node features based on information from all the neighbors, from all the neighboring nodes. And so now we've like embedded this into a new kind of graph with the same exact structure, but now updated information based on correlations. So then how do we use this sort of new updated graph of latent vectors? Of course, we can do node level tasks like identifying pilot particles or particle flow reconstruction, which is one of the examples I'll talk about. We can also take that latent vector and actually sum, again, aggregate it over the whole graph, and then use another function to get actually a single output per graph. In this case, we might do something like graph classification, for example, jet tagging, which is another example I'll talk about. And then finally, we can also do edge level tasks. So actually make a prediction for each of the links, each of the edges in this graph. And in this case, that's one of the most popular ones to do for tracking is that we try to predict whether these two nodes should be connected as part of a track. So whether this represents a good track segment. And so this message passing step is one of the most computationally intensive, but there's sort of actually many other steps in the chain. And so it's important to kind of consider all of them, to see where which part we're going to accelerate and which parts are computationally like a bottleneck. And so of course, you start with this like data pre-processing and graph construction. And again, this may or may not be part of the architecture, the graph neural network architecture itself. Typically, for tracking, it's typically kind of a pre-processing step, but for some examples I'll talk about today, it's actually part of the network. Then there's the GNN inference step, and again, message passing is sort of one of the most intensive because you're doing this neural network inference on every node and every pair of nodes. So it can be just by that fact, it can scale dramatically. Then, of course, there's aggregation and all these other steps that can also contribute, but are not as computationally intensive. Another one that can be quite computation intensive is if you have to do this dynamic graph building or rebuilding. So using something like k nearest neighbors or locality sensitive hashing, different tricks to try to like make this more computationally efficient. But nonetheless, you're still doing some sort of complicated kernel where you're trying to sort, let's say, all the nodes based on some criteria, like some distance in a latent space. And then do this, find all the nearest neighbors. So this could be a computationally intensive task. And then finally, there's post-processing, which I won't really get much into, so I'll focus mostly on the accelerating the GNN inference itself. Okay, so what are the challenges of this? So as I mentioned already, one of the challenges is just like the number of mathematical operations you have to do. So this, very, very roughly, this scales with the number of nodes and edges and the neural network sizes that you're using to do this inference. So the number of ops, for instance, typically it's dominated by this first term. So the number of edges is usually much larger than the number of nodes. So it's the number of edges times some sort of characteristic edge neural network size, the size of the neural network you're applying to the edges. And that's usually the dominant term. But of course, there's also this other term, which is often, you're applying a neural network to the nodes itself, perhaps to embed them into some latent space. And so that can also be, a big contribution, especially depending on the relative sizes of these neural networks. As I mentioned, so sort of for naive, fully connected graphs, of course, the number of edges scales as the number of nodes squared. So the scaling can get quite large very quickly. But of course, in most cases, we're trying to do some clever graph construction or reduction steps so that we're not essentially always dealing with a fully connected graph. And one other challenge is the fact that there can be this variable input size. So the number of nodes and edges are not fixed necessarily, and you can have a variable number of them. And so your algorithm, of course, GNNs kind of intrinsically can take this into account, but then you also need the hardware or the framework to be able to handle that. So you need to be able to handle this kind of dynamic axes. So a tensor, as input, where one of the axes is, a variable, essentially a dynamic variable. And finally, I'll talk a little bit about this idea of so-called ragged batching, which is, ideally it'd be nice if the framework or if your hardware can take into account the fact that even within a batch, for instance, you might have, for example, a jet you might have 10 jets in a batch, and they might have a different number of particles, each jet. So can your, algorithm, GNNs can typically take this into account, but can your, hardware acceleration framework take this into account? For dedicated hardware, like in FPGAs, one issue, of course, is this kind of non-static index access, which is to say that if the graph connectivity is not known beforehand, if it's a dynamic part of the input, it means that you're not necessarily able to, you need to be able to route any two nodes to be multiplied together, or any two nodes to be running inference on any pair of nodes. So this means that there's basically a lot of additional hardware that's being implemented that may not be used for any given example. Some of this can be done with like a sparse matrix multiplication engine that's kind of tailored for this, but this is just kind of another challenge. And then finally, for dedicated hardware, for like FPGAs or ASICs, thinking about the quantization strategy. So whether fixed point, integer quantization, or whether you use like a reduced floating point, like this bfloat 16. And there's, challenges actually with the dynamic graph or KNN steps, because as I'll talk about in a little bit, this can really limit, basically if you get this wrong, if you get which neighbors are the closest wrong, it'll kind of have cascading effects as you go down to the rest of the inference. Okay, so this is actually kind of like my thesis, and then as each of the case studies, I'll talk about one of these problems in more depth. But if you have actually questions, this may be a good time to stop and ask.
Controversial. Yeah, Javier. So you mentioned the scaling in the number of operations. Are you worried about the scaling in memory? Because that seems something which is also could also be an issue especially for what you want to do.
Yes, that's a very good point. I didn't mention that, but yeah, there's definitely two sides of this coin. There's operations is kind of the easy one to count. Memory is also relatively easy to count, but yeah, you're right. It's the memory, for both the inputs, then the intermediate results, and the final results can also be quite large, especially with, if we go back to, the different cases, it's, potentially not as bad for jet tagging or for graph classification, because usually your outputs are small. But yeah, for things like link prediction or node classification, you're essentially like returning inputs that may be even larger, or returning outputs that are maybe even larger than your input. So yeah, you do have this large memory that you have to allocate, basically.
So Xavier, can you elaborate more on that ragged batching?
Yes, I have a slide on that, so maybe I'll wait till then.
Okay, thank you.
Yeah. Anything else? Okay. Then I'll continue, and yeah, I have slides on these things. So for the first kind of case study, I'll just briefly kind of talk about what particle flow reconstruction is, just to get you on the same page, but then talk about how it can be accelerated. So in general, particle flow reconstruction is this task where you have these particles that interact with the detector, so they leave energy deposits and tracks. Particle flow is kind of like the inverse process of taking these signatures that you see, these clusters of energy and these tracks, and trying to combine them in a way to basically infer which particles left those traces, which particles left those signatures. And so as like a machine learning task, you have this input set, which is like this point cloud or this heterogeneous graph of tracks represented here by these gray lines. Ecal clusters, so clusters in an electromagnetic calorimeter, represented here by these blue blobs, and then HCal clusters, so represented here by these orange blobs. And then you can have sort of a target set of truth particles. Here we're just kind of showing characteristic placement, although particles are really these four momentum, so they're basically tracks, they're like tracks as well. And what you want to do is you basically want to take these inputs and assign them to some truth particle. And so you want to construct this mapping essentially for the output set, this predicted set of particles that minimizes some distance. So both, and really you have two kind of subtasks here. One is to identify the set of particles. So basically identify the type of them. So whether they're muons, photons, electrons, charged hadrons, neutral hadrons, and so on. And as well, you also want to figure out their momentum. So you want to be able to tell, what is their form momentum, basically. So you have these like two components of the loss. So one approach for doing this is this MLPF algorithm, which is a graph neural network. So you start with the event as an input set. Here I'm showing it as like a heterogeneous graph, but actually what we do is we essentially embed it in such a way that each track and cluster has the same dimensionality. So this is one way to try to deal with heterogeneous inputs, is you basically like pre-process it in such a way so that it has the same size. And there's actually many other ways to do this, so I can talk about that. We convert this input set into a locally sparsely connected graph, and this is done with this so-called locality sensitive hashing plus k nearest neighbors. And what that means is that basically the two steps here, locality sensitive hashing is basically like you first bin it in geometrically, so in like 8 of 5 space. And then of those, just like of this smaller set of nodes, then you apply k nearest neighbors. So this can sort of is a way to computationally improve the efficiency so that you don't have to do k nearest neighbors, let's say over the full set of nodes. Afterward, you can apply this sort of standard message passing once you've been able to construct this graph. And from that, you end up with a transformed set of inputs, like a new set of nodes with different features. Finally, you can actually decode this. We actually decode this with an element-wise fully connected neural network, so not really a graph neural network anymore. And then finally, we can compare to the target set and try to optimize this in order to get the correct mapping. And what we find, and this is shown in this paper, is that the classification performance is the same or better than the rule-based PF algorithm. This is on a study with Delphis, so kind of a simplified scenario. And also the regression performance is the same or better than the rule-based algorithm. But what I really want to get into is actually the scaling with the number of elements, because this is what we wanted to accomplish. We wanted to accomplish an algorithm that is inherently parallelizable, and once you have a GNN, it kind of is. And so what we find is that the model inference time scales linearly with increasing pileup event size, which is not typically the case for this for the standard PF algorithm. It usually scales non-linearly or quadratically. But so we have this nice scaling property, and increasing the batch size can also help improve the inference time as well. And since this is kind of natively implemented on GPUs, we can actually use GPUs as co-processors in our event framework, and actually use these GPUs to accelerate the inference, while the CPU can be doing other tasks that are sort of more naturally fit for the CPU. So I'll talk more about this, what this picture means on the bottom left in like a later slide, but just wanted to say that this is something we can apply this algorithm using this so-called inference as a service paradigm. And actually we have an updated, updated results for using actual CMS simulation. And this was shown in ACAT 2021. And so this is an updated model with actually more realistic inputs, which is from CMS. And so here you can see this kind of is going toward the question from Paulo actually about the memory usage. And so for this GNN, we actually have the memory usage here on the GPU, as well as the runtime, so the inference time per event. And as you can see, basically in this typical run-3 range, which is shown with this dotted lines, the typical run-3 event time is about 10 milliseconds wall time. And it takes about 1 gigabyte of the GPU RAM. So this GPU, for instance, has 8 gigabytes. So actually you could potentially do this with multiple instances of this algorithm. Although it's not totally apples to apples, this can be compared to roughly 100 milliseconds, which is what the standard PF algorithm is expected to need to run the inference time for a standard PF algorithm in run 3 conditions. So you can get an idea that this is quite a large speed up, about a factor of 10 speed up for this this kind of algorithm. Of course, using a GPU though. So one challenge of this kind of algorithm that I kind of mentioned already is, we were interested actually in trying to like accelerate this with even different kinds of processors, so for example, this Goya AI inference card from Intel. This card actually uses fixed point quantization. So it uses like 8, 16, or 32-bit fixed point. But there's actually some delicate issues, which is that it's basically all post-training quantization. But with this dynamic graph building step, of course, you need to make sure you return the same indices for the k nearest neighbor step. So you need to actually make sure it returns the same indices. And in this case, actually, if you quantize it, it doesn't necessarily return the same indices due to rounding errors and like truncation and overflow. And so this means that the rest of the GNN inference is essentially corrupted or inaccurate. So far, actually, we've seen that 16-bit floating point actually seems more promising, and probably bfloat, 16-bit bfloat will work even better. And so right now, actually, we've been able to successfully train using this 16-bit floating point. And so this is one issue, which is that in a lot of these new platforms, quantization is kind of assumed to work really well, because it does. It works really well out of the box for CNNs. But for GNNs, especially with this dynamic graph building step, it is not necessarily true that they work as well out of the box. And so one sort of workaround or one sort of solution to this is actually thinking about quantization during training. So actually applying quantization aware training and kind of co-designing the algorithm in general can circumvent these issues. Yeah. So I have another kind of, can take more questions now. I see Sammy has a question.
Yeah, Javier, just a quick question. So when you talked about the local hash, if you apply that local hash plus k nearest neighborhood and address the rounding of errors, isn't the local hash plus KNN is more unstable when you're prone to rounding errors compared to just a KNN?
Yeah, potentially. Yeah. So we are exploring that actually. We're exploring like, it is exactly, yeah, exactly what this last bullet point is that, we had designed the algorithm in a way that scaled well and worked well, but for floating point inference. And so if there is these like little twerks, there's little tweaks you can do to the algorithm to actually get it to run really well in fixed point, that is exactly like, I think the idea.
Okay, thanks.
Yeah. Dan, yes.
Yes, that's me. So for your graph neural network, your node is I assume is a particle, right?
Yes.
Yeah, from your particle approach. So then in this graph neural network, there may be two type of relationship. So when you have a particle, you have decay. And then you have further decay. So that means that from a parent particle to the child particle, you also have like sibling kins particles, that's geometry distance. From parent particle, the relationship is like give born birth to the child particles. So how do you differentiate these two different type of relationships? Actually, it might be actually very critical for you to identify that type of jets.
Yeah, that's a very good question. I should clarify that in the particle flow reconstruction, well, in general, in the traditional approach, we don't necessarily, that's not usually since you only really observe the final state particles,
okay.
This idea between this relationship between parent and child is not always observable, let's say. And so since we're trying to reconstruct the basically observable set of particles, we're essentially always trying to reconstruct the last children. So it doesn't necessarily come up in this case, but you're right. In general, this is actually an interesting topic because, for example, if we want to do simulation, or if we want to do generative AI models with GNNs, there is this different type of relationship between parents and children, and you might want to be able to simulate that. So you might be able to want to generate graphs with that different kind of edge structure. And I don't know if I have a good answer to that, but I think people have been thinking about this.
Then now I understand. So your basically the particle is actually represented by a track.
Basically, yeah.
Okay, got it. Thanks.
I hate to do this, but do you think you can wrap up in 10 minutes or so? 10, 15?
Yes. Yeah. In 10 minutes, I'll just end. Yeah. Sorry, Rustam, you have a question?
Go back to the slide in which you showed the architecture of your network. If you can hear me well, if not, I have to change my microphone. Okay. So here, yeah, I'm interested to know how many hits do you have as your, I mean, typically your events. How many nodes do you have?
Yeah, good question. So for this, the nodes, so the number of PF elements, so tracks and clusters, is typically of order like 6,000 or so, 5,000, 6,000. And then the number of output particles is of order like 1,000.
Okay, and do you have an input for the edge weights, for example?
An input, so like how many edges we end up with?
Or the input of this network is only some like values for the nodes, or do you have?
That's correct. Yeah, yeah. The input is only nodes, and then the edges are constructed dynamically. Okay. And it's a good question as to like how many edges are constructed. I'm actually not sure, but yeah, the point is it's not n squared. It's much less than n squared.
Okay, I see. Thank you.
Pei-Yang?
Yeah, thank you. Also, my question related to this. I mean, I'm probably the question is very naive. I don't know how to define the nodes and the edges, or it's the parameter, high parameters to optimize.
Yes. So the nodes are the inputs. So in this case, it's tracks and clusters and the features of those tracks and clusters. So the PT eta phi and energy and momentum, things like that. But then the edges here are basically constructed through this weighting through this this k nearest neighbors. So essentially, we're just choosing the nearest neighbors in either the geometrical space or some latent space. I think here it's a latent space. Yeah.
Okay, thank you.
Sure. Okay, so I will speed up. So another task is jet tagging. And like I said before, this is kind of a simpler task in the sense that the output is sort of as for the graph as a whole. Again, here for jet tagging, we might have multiple sets of inputs, so like particles and vertices. So here there's another way to essentially, rather than just like padding the two vectors to be the same size, we can actually do something else, which is essentially embed them into some common latent space, some common representation space, and then use that as the graph input. So then all of particles and secondary vertices can be considered together. One algorithm we use in CMS is called this particle net algorithm. This also has dynamic graph building, which is again using k nearest neighbors. And it has a very, very strong performance. So 50%, that should be 50% true positive rate for a false positive rate of 0.1%. Also, we can do this, you can use kind of this algorithm for mass, for the mass regression of the jets. So it's actually has good performance there too. So now let me get to like accelerating this algorithm. So the way we typically do ML inference in CMS-SW and CMS is we convert this model to ONNX, an ONNX model, and use ONNX runtime on the CPU. Because for example, PyTorch is not supported, which this model is written in. So we export this model to some computational graph with ONNX. Part of it is shown here. Then we can actually run it in our framework. And what you see is that this is a sort of, sorry, I should have highlighted here which part I'm referring to, but basically out of this sort of 1000 milliseconds or 1 second for processing time for this step of data processing called mini AOD, particle net, just running all these different flavors of this particle net algorithm actually accounts for about 43 milliseconds of the inference time. So about 5% of the total mini AOD processing. And of course, there's other networks that take up even a larger fraction. And then more and more GNNs are being developed to do different, to replace different tasks. So this is quickly becoming kind of a big fraction of the computing budget is spent on deep learning inference. And so one thing we can do to speed this up is actually use this paradigm of inference as a service, where these, rather than using the CPUs to do the inference, the CPUs basically just send the data to some coprocessor like GPUs, FPGAs, or dedicated AI processors to do the inference. So what this looks like is you can have this cluster of GPUs with some load balancer that controls basically which GPUs are used for the different inference. Then you can have your usual bank of CPUs. As they go and process a single event, they'll send the data for particular jet tagging or particular PF inference, and send it to some server, some remote server. That remote server will crunch the numbers, do the inference in a much accelerated way, and return the outputs. And because this can be done asynchronously, it doesn't block the CPU. So the CPU can go on and continue doing other parts of the computing workload, and in a way that's kind of synergistic for both of them. So one consideration for this kind of paradigm is that for GNNs, the inputs are not always rectangular. In fact, it's optimal if they're not rectangular. So, but nonetheless, to get them to fit into this paradigm, usually what we do is we the inputs are zero padded up to some standard fixed size. So this allows for sort of regular rectangular batching. So each object in the batch will have the same number of input elements. So if there's a jet, if you want try and do this inference on jets and they have like 5 particles, you'll pad all the jets to 5 particles in order to do the inference. However, this kind of incurs kind of unnecessary operations because there's just a bunch of zeros that are being added that then don't affect the result, and you're just kind of wasting GPU computing. So to reduce both the memory and the computation, the framework can allow a variable size input graph within a batch. So the idea is that you want to be able to allow this sort of ragged batching. So different objects in the batch will have different number of elements, and then you can run inference on these different sized elements. And so I just wanted to show here one sort of result plot showing that the inference time can be accelerated dramatically by using these GPUs to do the inference. And actually, this is an unfair comparison because the ragged batching I was just mentioning, we haven't finished the implementation yet for the GPU, this inference as a server with ragged batching. So this is doing this zero padding. So it's kind of the GPU results have this, we know that they're worse because of this. But nonetheless, the CPU inference throughput on a single CPU core is about 500 events per second. Whereas for this, running this on a T4, we see that, and this is just a few different tests, but the one you can focus on is the red curve there using the native PyTorch model. That the native PyTorch model, depending on the batch size, we can actually improve this throughput up to 10,000 10,000 events per second in terms of throughput. Of course, this is like an extremely large batch size, but still you can kind of get the idea that the gains to be had are quite large. And also the latency can be dramatically, can be much smaller than what we have on a CPU. And then of course, this story gets even better, the more expensive GPU you have. So moving from a T4 to a V100 improves the performance roughly by a factor of 2 to 3. Okay, I'm just gonna speed through the last part, which is of high interest to the workshop. So there's a lot of interest in using FPGAs for GNN inference. And there's many use cases like charge particle tracking for the level 1 trigger or for co-processing with an FPGA. And the last couple of years, there's been really just an explosion in the literature of people, especially like CS people and ECE people, exploring hardware acceleration for graph neural networks. This is just a link with just a small subset of these different papers, all proposing a new kind of system or new kind of accelerator workflow for accelerating these GNNs. And so I think it's worth actually exploring all of these solutions because we don't know which one of these is actually going to be the best for our use case. Nonetheless, we actually did develop our own kind of in-house implementation. And so this is using an interaction network for GNN for tracking. And we developed kind of 2 models. And this is actually already talked about during the workshop in Abdel's talk. And there's this paper you can check for more details. So I'm not going to go into too many details here. But basically what we do is rather than kind of programming FPGAs in the standard way with like RTL, which looks something like this, we can actually leverage this simple interface, which is HLS. Essentially, HLS code resembles C++ in order to program the FPGAs. And most of us are much more familiar with this kind of way of programming. And moreover, we can actually abstract this away even more, one level up, and say, just basically prepare a bunch of kernels, C++ kernels for different kinds of layers, and then have the user just specify an AI model, a specific kind of neural network model, which can then be replaced with the C++ kernels that can be run on an FPGA. And so what this looks like is this package HLS for ML, which is this user-friendly Python package for transpiling ML models into this HLS code and FPGA firmware. We actually get decent results for this in terms of the accuracy. So in here, I'm just showing that we can actually also do quantization-aware training so that we can actually reduce the number of bits required for the inference and still retain good performance for the model. For our throughput optimized, this is like the trigger-based model. We don't necessarily scale to very, very large graphs with our implementation, but it does fit on an FPGA for, a small number of nodes and edges. So in this case, order of 30 nodes and 60 edges. And it does fit in the latency requirements for the trigger. So this might be something that is good for, so for example, tracking in a muon chamber and muon chambers where you have like obviously much less nodes and edges than in some other system like in the tracker. Or if you can sort of segment the event enough. On the other hand, we have a resource optimized design that can scale to thousands of nodes and edges and fits on the FPGA. So this actually might be more useful for co-processing applications because the latency is too long for the level 1 trigger, but nonetheless can still be quite useful for things like high level trigger or offline processing. For further improvements, I didn't mention anything about the graph construction stage, but this can also be accelerated on an FPGA, and you can see more about this in Liv's talk from the workshop. In this case, the graph is dynamic per event, but is considered pre-built and fixed up to, and like the maximum size is set. But we didn't have any physical restrictions taken into account as to which nodes should be able to communicate. So obviously for tracking, nodes that belong to neighboring layers are the only ones that can really communicate. So taking that into account can actually reduce the resources and imposing So to summarize, to accomplish these HL and LHC goals, we need to tackle this extreme computing challenges. GNNs for event reconstruction can improve the performance of our detectors and save potentially overlooked data. These special hardware processors can accelerate inference and training. And there's actually many common challenges to consider. And recently there's been extreme interest and a lot of exciting work in this space. So I hope to discuss this all with you. Thank you.
Sorry, we clapped.
I can see.
Wow, what a talk. Do we have any more questions? I see people have been asking questions, which is a good thing. Liv.
Yeah. Hi, thanks for the super nice overview. So I was wondering, so all of these tasks, they seem to do quite well, but it's kind of separate. Has there been any thought given to kind of combining some of these methods into one so that a graph neural net could do several things at once?
Yeah, that is a really good question. Yeah, there's kind of two ways to take that. One is, to think about doing this kind of like foundation model approach, the way that in industry, people have been moving more toward like these large models that are pre-trained on data, and then thinking about adapting them to different tasks. I think that is a really interesting area of research. The other way to take that is actually having, if we can converge on a kind of specific kind of GNN that does, reasonably well for many different applications, we can actually consider, making a like ASIC essentially for that GNN, right? We can consider making, maybe not totally customized, maybe reprogrammable, obviously reprogrammable weights, but or even just having an FPGA implementation that's like, out of like off the shelf that many people can repurpose for their GNN. Exactly. So then this idea becomes like, if we all kind of can congeal on the same kind of GNN, we can actually like, accelerate it, basically share how we accelerate it and use that in many different places.
What are the roadblocks to doing that, do you think?
Well, one is that it's hard to get everyone to agree on even just like what to call the same neural network. So I think having everyone agree to use the same exact architecture, let's say, is actually a big challenge. Everyone's using their own framework, PyTorch geometric, DGL, JAX, Giraffe. So there's lots of different frameworks. And so, I think it is this unified view. It will take a while for us to kind of explore all these different options and then see like, oh, this is a kind of universal solution. because I think there's just so many different choices that we can explore right now that it'll take a while.
I think,
Yes.
Kavi, I think the one of the inputs for this will also be a standardized language to describe the graphs, right? I mean, at the end, it's there is a lot. You mentioned Onyx. I think that's quite has a graph description as many, and I think that would already help a lot. Yeah, that some node edge. I mean, at the end, it's the same, but all over in different, slightly differently flavored and nuanced versions. And that could be a good step towards it, because then you could sort of try to decouple a little bit the actual, let's say, framework implementation from the description of the graph.
I 100% agree, and this is actually something that the student I'm working with is currently looking at, which is exporting different GNNs to Onyx, to a standardized Onyx format. So I think that is actually one thing we could all work on together. That's very exciting. Yeah,
also I think if we push, Onyx is very much, I think, at the lead at this for the moment in the usage. If we then kind of, you know, conventionally, somehow one needs to start conventionally by convention, start using it in a similar way between the different groups that are contributing to this research, then that could give a momentum towards a bit of a standardization.
Yeah.
So I'm the bad guy today. We should move on, because
Okay.
and also because